Welcome to our mini-series on practical glaze basics. Once or twice a week I get some really basic questions on glazes, and a lot of times they center around glaze basics, and the interpretation or misinterpretation of the basics causes people to hunt and search and really find glazes difficult, and they are not. So the basis for this started with a spreadsheet created by Matt Katz, and he distributes it on his website. And then with his permission, we took the sheet and we added some automation, some simple Visual Basic code to allow you to have some convenient buttons to print and time tag it and whatever. Tab around the sheet a little easier and increase the fonts. So our changes were minor, but we got his permission and we distributed as well to a whole group of folks that are part of the glaze group. So anyway, after all the questioning, I decided, there's got to be an easy way for folks to learn glaze basics, and why not just use this sheet as a basis? And then if I were going to use a sheet, I got to talk a little about Stull. And Stull looks very complicated, but Stull was a guy in 1912 who decided to figure out how glazes work, and so he created this mat. After a bunch of tests, he put all his glazes in a certain order using UMF, the unity molecular formula, and as a result he made the chemistry visual. So that made it easy for ordinary people to look at this and find a dot that's right there, and for them to say, it should be a glossy glaze if we fire it to the right cone temperature. And that is true. So that idea is more significant than you think. So let's take a look. So here's our spreadsheet. Here's Marcia's Hard Candy Clear. And in this case, we got it out to a gloss. We know that because it's near that line. And so this spreadsheet shows you the Stull map, and it breaks down the certain chemical analysis that you need to know, mainly silica to alumina ratio, which is the predictor of matte or gloss, the metals in the earths, which are the flux ratio, which we'll talk about later, and then it allows you easily to put in your ingredients, then it normalizes them to 100% for you, then you can designate a batch size and make your glaze. The sheet also does the UMF for you, so you don't have to be a chemist. And the UMF really shows you that in this recipe, Custer's given me 25 grams of silica from the Custer, 20 from the flint, 8 from the frit, 2 from the APK, and so on and so forth. So all of these ingredients have components in them, and the components, the chemicals, the base chemicals, make up a glaze. So a glaze is really just a bunch of chemicals. So UMF quantifies this for us, and then it puts it in this spreadsheet on the map, and the map allows you to, at a glance, look at it and say, oh, I know a bunch about this glaze and how it should react. So let's detour a little bit about Stull. So Stull was a genius. He used UMF to plot his stuff. He created this graph, alumina here and silica there. And then he realized, it's this ratio of alumina to silica that determines whether it's matte, gloss, more glossy, underfired, crazed, unfused, you name it. So 5:1 for a silica to alumina ratio line is usually matte. Below that's for sure matte. Above that turns to gloss. And you look at this and you go, well, it's pretty mundane. But it's actually pretty significant. If I have a glaze with a 5:1 silica to alumina ratio, and I simply add silica to it, and here let's look at this in our chart. If we go from 3 to 4 in silica, if I add that much silica, I've taken a matte glaze and made it a gloss glaze. And guess what? It really works. So let's take a look at that for a second. All right, here's Marcia's mat. In its base form, it's just under 5:1 for a silica to alumina ratio. There's the dot in the little semi-matte area showing us less than 5:1. There's the fired sample to count 6, which is what it was designed for. And in this case, this picture shows it to be glossier than it is, but it's a true matte. And we take, knowing Stull, we say, if we just add some silica, some of the folks here want this to be more satin, not matte. So what does that mean? That's all, a taste. But we do know from Stull that if we just simply add silica and keep firing, we'll find something in between matte and gloss that somebody's going to like. So just to test that out, we add 6 grams of silica, we fire it again, and guess what? It's now satin and slightly glossier. And we can keep doing that all the way through, but we decided, you know what, let's find out if Stull is right. We're going to trip them up. We're just going to add 20 grams of silica, get this silica to alumina ratio to 6.60 to 1, or close to 7 to 1, which should make it glossy. And let's fire it and see what happened. Oh, yeah, it did turn glossy. He's right. So Stull does tell you at a glance what a glaze should be, and then you can always confirm it by doing this, and this kind of confirms that we're firing this in the right range as well. But anyway, just to illustrate, this stuff really works. This chart isn't fake. If you move from this amount of silica to alumina ratio to here, it goes glossy, just like the map says. So, to that end, there's some real basics that are very mundane, but you gotta learn them. And I see a lot of mistakes because people don't know the basics. So I figured I'd write down 7 basics I think you need to learn. Number 1, how do you make a glaze? What does a glaze consist of? Silica, alumina, fluxes, and colorants. Silica is the glass former, alumina is the refractory. Neither of these two guys will melt below 3,000 degrees, so we need fluxes to help them melt. And then colorants, oxides and stains to color your glaze and make it pretty. So that is a glaze, period. 2, and this isn't necessarily a result of glaze chemistry, but I see this mistake all the time. I see this bentonite everywhere in every ingredient. We like to add clay to our glazes for a couple of reasons. One, we like to use the silica and alumina in the glazes efficiently, so we don't have to go elsewhere to get them. But turns out 10% glaze in a 10% clay in a glaze keeps it suspended, or helps keep it suspended. So if you have less than 10%, there's a good chance your glaze won't stay suspended. If you have 10% or more, there's a better chance that it will stay suspended, which means it's workable and it'll stay in a bucket and you can mix it up and dip your ware and it won't just sink to the bottom before you can do that. If we don't have 10% clay in a glaze, then we oftentimes add up to 2% bentonite just to help keep it suspended. So bentonite's not really a magic ingredient to make the glaze look some way. It's just added because, gosh, we couldn't figure out how to use a natural clay and get 10% of it into our glaze and be useful. So rule number 2 on my list is know why we like to have 10% clay in a glaze. Number 3, the Stull chart. Guess what? It indicates what the glaze will look like, or the glaze chemistry should look like, fired to the proper cone. So will it be matte? Will it be gloss? Will it be underfired, overfired, or crazed? That sounds silly, stupid, easy, but it helps people. If people would commit that to their thinking, it helps you diagnose what's going on with the glaze when things don't work for you. Number 4 is super important, glaze durability. There's a lot of debate on this. None of us have scanning electron microscopes in our backyards. So how do you know a glaze is durable for functional wear? And we're just going to declare there's a good flux ratio that indicates a glaze is durable. Outside that ratio, it's probably not durable and probably not for functional wears. It can be artistic all day long, but it's probably not going to be the most durable. The lemon test is not very good. often water and soap, far worse. So, yeah, I know we all think lemons are bitter and strong, but a lot of times our glazes don't care. Our glazes just wash away in the dishwasher instead. So dishwasher and alkali soaps will erode your glaze mostly, probably throughout their life. And there's plenty of other stuff. You stack your plates on top of each other, they rub each other. Cutlery, you use knives and forks and sharp implements, and that's all a problem, and it will wear away your glaze. But far more problematic is the dishwasher, actually, and the biggest problem is, how do you know it's durable? And now you have to memorize the flux ratio to know that it's likely most durable using simple range of ratios. So, flux ratio, durability. This is a huge breakthrough, right? So these are the fluxes that help your silica and aluminum melt. And this is an R2O flux or an alkali metal, which all the purples are lithium, sodium, potassium. You get what's going on here. All the ROs, or alkaline earths, are in the blue: magnesium, calcium, strontium, barium, and zinc. So this ratio of this to this, which always adds up to 1, is the flux ratio. The durable portion of it is when the R2O is between 0.2 and 0.3. Period. So it's pretty easy to remember. And since they always add up to 1, you really don't have to remember the other number, because it's always 0.9 plus 0.1 is 1, 0.8 plus 0.2 is 1. So now 0.3 to 0.7, a very durable ratio, equals 1. So if I just remember, my R2O needs to be between 0.2 and 0.3, and as we start to get way outside of that, it becomes less and less and less durable. So for functional wear, a nice durable ratio between 0.2 and 0.3 is a good thing to start to know and commit to. So that's number 4. 5, 6, and 7 are going to be boring. 5, if a glaze is overfired, it runs. Period. The end. Okay. It melts too early for the amount of silica, alumina, and fluxes in it, and gravity takes over, and it runs down your pot. Now, you get people who argue out on the edges of this. They go, well, it's a cone 6 glaze, and I fired it to cone 10. Well, it ran. It melted too early for the amount you're firing it, or it melted too early for the amount of silica, alumina, and fluxes in it, and gravity took over, and it went down your pot. And guess what? Now you know it's probably a cone 6 glaze, not a cone 10 glaze. So now you've diagnosed it. So if a glaze is, if it runs, it's over fired. Okay. If a glaze is under fired, guess what? Well, it's probably not fully melted. It might appear matte, even though Stull says it's a gloss. So, looking at Stull and assuming Stull is right, if I see a glaze that's a gloss in Stull and I fire it and it's a matte, that's telling me what? It's probably under fired. We see this all the time. We see folks take cone 10 glazes, fire them to cone 6, and they go, what a lovely matte. Well, it's just not fully melted. So, if a glaze is under fire, it's generally not melted. So, that's just something to commit to memory so I don't make that mistake. And then you can apply it as you would fly. So, if you're doing sculpture, you're not doing the inside of a pot, and you want to have an underfired mat on the outside. Will it be durable? Probably not. But there's no law against it, right? Just as long as you know what you're doing. So overfired and underfired glazes are likely not as durable as their flux ratio indicates. Because remember, the flux ratio and that whole thing on that spreadsheet indicates what should happen if it's fired to the proper temperature. So overfired equals overmelted, underfired is not fully melted. That's that. The one that you really need to remember, boron is a thing. Too much boron is a bad thing. Not enough boron means you won't melt. So Katz derived this. I think he's the only one that did, and it's a pretty linear relationship. And he provides this in the base glaze spreadsheet, so it's done for you. And so the thing to remember is cone 6 is about 0.18, so somewhere plus or minus 10% around that number is fine. Cone 04 is 0.45 boron, and it'll show you with the dot over there if you're working at cone 04. Cone 10 requires no boron to melt. Glazes are cone 10 to start with, and then we generally add boron to make them melt lower. So know these ranges of numbers, because too much boron is a bad thing, and so there is such a thing as too much boron. So that's number 7. And let's look at now what we know. This is a formula, a studio formula. It should be a high gloss, right? And we know that because if we can see the dot on the chart, but if somebody just told us the silica to aluminum ratio is 7:1, so it should be a gloss if it's fired correctly. Flux ratio is 0.5 to 0.5. We know it's likely not durable. Okay, that's just what it is. It's not, so for functional wears, I probably would not use it. And it's a cone 6 glaze, right? And it's got 0.42 boron. Well, that's crazy. So that's no good. So too much boron might explain why it's way too glossy or way too runny, or it might artistically allow people to move the glaze around and make it look nicer, but too much boron is not a good thing. So we do know that. Get another studio glaze. It's got a crazy silica aluminum ratio, right? Crazy. Its flux ratio is not the worst. It's closer. But look at the dot. It should be crazed. It's not very good. One of the things, it doesn't have much alumina, which gets it down to this crazed area. It's got a crazy amount of boron in it as well. This glaze should be glossy, but it fires kind of muddled, matty, not melted, over melted, who knows. Is it durable? No. Yeah, I wouldn't say it is. It is what it is. Would I use it as a durable glaze? No. So it's got some problems, and we can spot these right away. Why these have so much boron, we don't know. A lot of times people used to put in 10 or 20 or 30% Gerstli borate and say, oh, there you go, that'll do it. But we know that's too much. So not the best chemical formula in the world, and more of an artistic formula if you ask me. Let's look at this one. Oh, Celosia copper red, our first cone 10 glaze, and not a bad flux ratio. Kind of a high silica to alumina ratio, but that's because alumina is low, but not so low that it puts it in the crazed area, so that works. And very little boron, and that's okay. It's not the end of the world. It almost doesn't exist. And whoa, wait a minute. Let's look at the list of this stuff. And bentonite too, my favorite. Let alone 1.45 bentonite. How'd you come up with that number? This is what happens. People try things and they have no basis, so they just keep adding things and firing. It's a valid way to test, and it ends up to be, yeah, it's an okay glaze, and it's probably durable, and it's probably a huge waste of material, because I think you could make this glaze with maybe 5 of these base components in the same colorants, and it's been done. But over the years, you could see what happened is they just added and added and added, and finally ended up with a million ingredients. So who would want to mix that all the time and waste all that natural ingredient? But whatever. I mean, it will fire. It does. It ends up glossy. It doesn't seem to craze, and it does reduce. So I would probably get a better, more truncated recipe than everything in the kitchen sink here, but it's okay. So that's how these things evolve through trial and error. So if you want to correct it, you can correct it and work on a glaze with 5 ingredients that gets you the same or better results. So common glaze faults. So those are the basics. We're not going to do too much on glazes, but common glaze faults, we got to talk about faults. because you hear people say crazing. Crazing is because your glaze shrinks faster than your clay, period. So if it shrinks a lot faster, then you get big cracks. If it shrinks just a little faster, you'll get micro cracks. The interesting observation is a lot of folks, think, well, I put a padlock on my kiln. I didn't open it for 3 weeks, so everything would cool off really slow, so nothing would craze. And that may work in the short term, but if the fit is bad enough and it's going to craze, it will craze. It doesn't matter if it's a day, a week, a month, or a year. And actually, when they test for things and try to figure out if they're going to craze in a week or a month or a year, they do some crazy tests. They'll put it in boiling water and put it in the freezer. So, if it's going to craze, it will craze. That's one thing we can say for sure. Shivering's the other side of that. The clay body actually shrinks faster than the glaze, and so often you'll see the glaze pop off the pot because the clay body is shrinking faster than the glaze can. So then once it exceeds the shear strength of the glaze, it just simply pops right off the pot and you get a shiver. There's a million other glaze faults, but pinholes are the next most common, and there's so many reasons to tell you about those or to work on those that you need to take a glaze course or two or work on your own pinholes and solve them, and you'll realize that it's a pretty complex problem to solve those issues. So, but those are some common faults that you'll hear people around the studio say, and then you'll hear some common things like, oh, well, pinholes, take it up and, hold it for longer so the glaze will smooth out, and then it'll heal up the pinholes. And, it happens to be a glaze that doesn't have enough silica in it, so it's actually drying out and can't heal itself. So now you do a 2-hour hold and it becomes a Ronnie glaze with pinholes in it. And you go, I don't know what's wrong with this. It must be the glaze. So there are many problems. But as you know, the better you know your basics, the better your diagnostics become. So that's the purpose of introducing you this way. The basics will cover, 50, 60, 70, 80% of your needs. So it's time to analyze and fix. Let's see, all fixes are confirmed by trial and error testing. So all of clay is kind of like that. You create something, you look at it chemically, you know what it should do, then you fire it and you confirm it does that, and then you keep testing. So the 7 rules we want you to get today are: glazes are made of silica, alumina, fluxes, and colorants. Simple, but that's it. We try to use 10% clay in our glazes to keep things suspended in the bucket, not for some other magic reason. We locate, install, and see what the chemistry should fire to, and that's what it should fire to. Now, if you overfire it, it runs. If you underfire it, a gloss that says gloss install becomes matte. Guess what? It's underfired. Flux ratios are your best indicator of durability for functional wear. So at a glance, you could tell when things are functional or artistic. So you should know that. Overfired stuff is runny. Can't say that enough. Underfired stuff is not fully melted. And proper amount of boron is a thing. Too much boron, not good. Too little boron, you probably don't melt. That's it for now. This is the introductory. It may seem simple, but I'm kind of glad we solved went from matte to gloss, just to show you how easy a lot of this stuff is. And once you commit these things to being fact, then your diagnostics becomes way better and easier. So in future videos, we'll take one at a time and we'll show you from start to finish how we solved, X, Y, and Z, and oftentimes they appear to be extremely complicated problems. When we reduce them to the basics of Stull, they become very easy to solve. So that's the goal here, is get you introduced and interested. And of course, glazes are like anything in clay. You can go as far as you want. They can be as complicated as you can as possible, because there's an infinite number of conditions for each glaze. But the basics are the basics, so you got to start there and have some sense of a basis to start from, and that's what this is going to be, we hope. So anyway, hopefully you enjoyed it, and hopefully it inspires you to learn a little more, and we'll make a few more videos, see how this goes, but we'll make a few more fit or repair videos on glazes and show you how easy that is for many of the repairs. So I think that's it. I hope you enjoyed it, and I hope we see you in the next video.